Ever wonder how AI learns to make smart decisions, like a self-driving car balancing speed, safety, and comfort? Or how a robot learns to walk without falling over? That's the magic of reinforcement learning, RL, where machines learn by trial and error. But what if they can't experiment in the real world? That's where offline constrained RL comes in, using pre-collected data to train AI safely, but with a big catch. The data might not have all the answers. Today, we're diving into a breakthrough that solves this puzzle, using math so clever, it's like teaching a robot to solve a maze with a broken map. Let's start with the basics. In traditional RL, an AI explores an environment, trying different actions and learning from rewards. Think of it like a toddler learning to ride a bike, falling a lot but eventually getting the hang of it. But in real-world scenarios, like training a self-driving car, this trial and error can be dangerous. That's where offline RL steps in. It uses data from past experiences, like logs of human drivers, without letting the AI fall in real time. The problem? The data might not cover every possible situation. It's like giving a robot a map with missing roads. How do you teach it to navigate when the path isn't there? Enter the research we're talking about today. The team from the University of Michigan tackled this issue by addressing partial data coverage, the gaps in the dataset. Their solution? A primal-dual algorithm, inspired by a mathematical technique called linear programming. Imagine you're solving a puzzle where you have to balance multiple goals: speed, safety, and comfort for a self-driving car. The algorithm acts like a coach, optimizing for the main goal, speed, while ensuring the other constraints, safety, comfort, don't drop below a certain level. But here's the twist. Traditional methods either needed fully exploratory data, which is rare, or relied on complicated tricks that slowed things down. The researchers introduced a mild realizability assumption, a check that ensures their solution is optimal without extra steps. This keeps things efficient, achieving the best possible performance with letter 3F52 sample complexity. Think of it as a shortcut that lets the AI learn faster without sacrificing accuracy. Another key breakthrough. They avoided needing to know the data-generating distribution, the rules of the environment. Previous methods required this, but their approach uses a Lagrangian decomposition trick to extract policies directly from the data. It's like solving a puzzle without knowing the full picture, just using the pieces you have to infer the rest. Why does this matter? For real-world applications, this means safer, more reliable AI. Imagine a medical AI that balances diagnostic accuracy with ethical constraints, or a robot that follows strict safety protocols. This research paves the way for AI that learns effectively from existing data, without risky trial and error. Now let's break down the math. The team used a saddle point framework, a concept from optimization theory where the AI's strategy and constraints reach equilibrium. Think of it as a tightrope walker balancing performance, winning a game, and constraints, not cheating. They proved that under certain conditions, the AI's strategy isn't just good, it's nearly optimal and nearly feasible. That means it's super close to the best possible outcome while still respecting rules. How did they prove this? They started by assuming the AI's strategy was within a small error margin of the perfect balance. Then they tested it by tweaking variables, like ignoring constraints temporarily, to show the AI's performance stayed within that margin. This is called near optimality. For feasibility, they analyzed how much the AI's actions deviated from the rules, and proved those deviations were also bounded. It's like a driver staying within speed limits even when distracted. The real game changer. This approach works even with partial data, like a robot navigating a maze with only old maps. Traditional methods struggle here, but the team's PDORL technique handles gaps in data efficiently. It uses a smart learning strategy that adjusts step by step, minimizing mistakes over time. The result? A system that learns safely, even when it can't explore new paths. So what's next? The team's work sets a new standard for offline constrained RL, proving that even with incomplete data, smart algorithms can achieve optimal results. It's a step closer to AI that's not just powerful, but also trustworthy. Thanks for watching. If you want to explore how these ideas shape the future of AI, hit subscribe. And drop a comment below. What AI applications excite you most? Until next time, keep questioning, keep learning, and stay curious.